The next thing to talk about are equipotential curves. Sometimes these are called equipotential lines. The key idea is that every point on the curve has the same potential, and that's why it's called equipotential. If you had a point charge, a positive point charge, then if we place a negative point charge nearby, you might remember from the electric field lines that the electric field lines go from positive to negative. And so there would be one going straight towards it. There would be another in the region right around a point charge. Of course, the electric field lines all go straight away. They're perpendicular to the circle, the radius. Like they radiate away. They're lined up radially. And close to a negative charge, they would actually go radially inwards. And when you put these two things close together, what happens is that they influence each other. So you would get a curved field line on the top. You might get another curved field line coming down like that. And so the electric field lines here are shown in red. Very close to each point charge, when it's far away from the other one, what happens is that you end up with the potential being defined by the distance from the point charge. And so very close to it, you would have a circular equipotential line. And then as you get further away, then you might have it influenced a bit more like that. The key idea is that every point on these equipotential lines, these blue lines that I'm drawing, has the same potential. And the distance between equipotential lines gives you a sense of how quickly the potential is changing in space. When you have a positive charge and a negative charge close together, you end up with basically a straight line in between them. And I'm just going to label that as 0 volts. As you get closer to the negative charge, then the potential decreases. And I'm going to arbitrarily call this negative 10 volts. The next one would be negative 20 volts, and then negative 30. And that really is arbitrary because this drawing is not to scale. As much as I try to be a skilled artist, you know what the truth. I'm just good enough to try and explain these concepts. Essentially, though, the distance between these lines is meant in this case to represent a difference of 10 volts. And so where the lines get close together, then the voltage changes rapidly in space. But if I actually just switch to green for a second and look at this region going, say, from the negative charge down, notice how the lines get further apart. And so initially, when you're close to the charge, the voltage is increasing because you're going from the negative away. And the change in potential is quite high for a small displacement. But then as you get further away, the difference or the distance between negative 10 and negative 20 is much bigger. One of the key ideas here is that equipotential curves are perpendicular to electric field lines. So anytime an equipotential curve in blue crosses a field line, it should actually be perpendicular. And so I've tried to do that here, and we just try our best, basically. When I was teaching, we did a lab related to this, where we actually set up an electric charge distribution and then would measure the voltage at different points. And then after that, you would actually connect the dots, basically. So you might get a whole bunch of points with a voltage of 3.1 volts, and then you would connect the dots to get an equipotential line. And then you might have another one at 3.5 volts. Or in this case, you might have, say, 0 volts, negative 10, negative 20, and so on. And then after that, you would try to draw in the field lines and remember that they're perpendicular to the equipotential lines. Another thing to notice, another key idea, is that the electric field lines point towards lower potential. In terms of topographical maps and geography, if you're hiking in the mountains, it's kind of thinking like water flows downhill. And it doesn't really care, right? It's just following gravity. It's going downhill in the most direct way that it can. So with a similar analogy then, the electric field is pointing downhill in terms of potential. And the electric field is always perpendicular to the equipotential line.